Hello friends, we will begin with the third module on AI that is called state space 2. We have already seen how a problem can be represented using a state space and move around in state space and so on and so forth. We have looked at two trivial problems in the previous module. We have looked at a problem called 3-4 gallon water jug problem and 853 gallon milk jug problem, and we have shown how those problems can be represented using state space and so on and so forth. In fact, we have not stressed on one very critical aspect of state space called prerequisites. You cannot apply any rule anytime. Every rule has some prerequisite. Only when those prerequisites are met, you can apply that rule, otherwise not. In fact, when the rule is pretty specific, the prerequisites are pretty specific, simple. When the rule is complex, we have seen that we need to write less number of rules which are general. When we write general rules, the problem is that there has to be something. In fact, there is a single rule which is possible to be applied in many cases. And in fact, we have seen that in the previous example, we have used variables like x, y and z. So, what are the values of those x, y and z? How can the move assume that value? Because depending on those values, you can determine whether it is possible to apply that rule or not. For looking at that important characteristics of moving around in state space, we have taken one more, or rather two more examples here in this particular module. What we are going to do is we are going to look at a problem called missionary cannibal problem. Here we have 3 missionaries and 3 cannibals on one side of a river, and there is only one boat available which can only carry 2 people across. Everybody can row the boat, so it is not a question who can, everybody. What the requirement is that at no point of time you can have number of cannibals more than number of missionaries on any bank of the river. If it is the case, they are going to eat missionary, and this is something which we do not want. Now, this is the problem. Now, the first thing we have to do is to write the state space of it. Okay, so let us move on. Let us see how can I write the state space, and this is going to be much more complex than the previous case, little more complex. Okay, you have to have prerequisites, you have to have variables, you have to have some values, constraints on those values here. So let us see what we can do. Here is the description. Look at the slide. 3 missionaries and 3 cannibals to cross a river with only one boat. Boat can carry maximum 2. At no point of time the missionary should be less. Okay. And okay, now this is the state space representation. Look closely at this representation. L, M1, M1. L is the side of the river, the left side of the river. M1, C1 is number of missionaries and number of cannibals, and obviously indicates end. R indicates right, the right side. Missionary, M2 is number of missionaries on the right side, number of cannibals on the right side. Okay, and BL or BR, BL means boat on the left side and boat on the right side. Now the preconditions. Now you please understand, state space representation means I am defining all states using the simple formula. We have M1 missionaries, C1 missionaries on the left side, M2 missionaries and C2 cannibals on the right side, and either boat is on the left side or right side, where M1 greater than or equal to C1. Now that is the requirement. We have already seen number of missionaries must be greater than or equal to number of cannibals, but that may not be true if M1 is 0. Okay, so if you write a mathematical equation and when you are representing a real world, this is something which is tricky. Please remember to write M1 equal to 0, otherwise you cannot solve this problem, because when number of missionaries become 0, you can have number of cannibals as 2 or 3, no problem, because they are not going to eat that missionary. There is no missionary actually. Okay, and similarly M2 is greater than or equal to C2 and M2 equal to 0. Okay, otherwise. So that is precisely describing our requirement. Number of missionaries should be more or equal to number of cannibals on either side of the river, and then M1 plus M2 is 3 and C1 plus C2 is also 3. So no state will have number of missionaries other than 3 number of cannibals other than 3. Okay. So, this is an example of representing state. There is no complexity here actually, the complexity lies in the moves. So, here the symbols are explained, the next slide. Let us move on, and this is something which I have already explained. So, I will not spend time talking about this. Okay. Now, looking at this description, let us see whether this particular state, whether these states are valid or invalid. Let me know. L20, R13 and BL, is it valid? Okay, there are a lot of things. M plus L, 2 plus 1, 3, 0 plus 3, 3. Okay, number of missionaries, number of cannibals, great, they are still 3. But the other requirement, 3 is greater than 1? Yes, that is not allowed. Number of missionaries are more than number of cannibals is not allowed. So, this is an invalid state. L33, R00, is it a valid state? Check it. Number of missionaries 3, number of cannibals 3, acceptable, and number of missionaries and number of cannibals on either side of the river, you will not find number of cannibals more than number of missionaries, great. So, this is a valid state, fine. Okay. What about this state? Number of missionaries and number of cannibals, again you can see that is quite similar to the state that we have seen before, this one. Okay. It is a valid state. In fact, you can see that this is the initial state while this is the final state. We want all missionaries to move from left side to right side. Okay. So, this also is a valid state. What about this? Okay. Number of missionaries on either side is less than number of cannibals, but number of missionaries, calculate, 2 plus 0 is 2, they have to be 3. So, this again is an invalid state. Okay. So, this is something which is about prerequisite. Okay. We are looking at the prerequisites, see that. Okay. Look at this. See the prerequisites, there are 4 prerequisites in the state space representation, M1 greater than or equal to C1, M1 equal to 0, or M1, M2 is greater than C2, or M2 equal to 0 and M1 plus M2 equal to 3, C1 plus C2 equal to 3. These are 4 prerequisites and all 4 of the prerequisites must match. Okay. Then and then the state is valid, otherwise the state is not valid. Okay. Let us move on. Let us look at, okay, the rule number 1, moving from left to right. You may be surprised, the earlier example we had 12 moves. This is a harder problem, but we only have 2 moves. Great. See, now try to understand. It is L M1 C1, R M2 C2 and BL. Okay, let me tell you one more thing. This is my way of representing. There are 100, almost infinite number of other ways to represent this problem. And the next example, I will show you there are 3 different ways of representing the same problem. So, that does not mean, it does not mean that this is the right way of doing it. This is just one way of doing it. Okay. Looking at, keeping that thing in mind, let us look at this. L M1 C1 and R M2 C2 and BL. What does that mean? It says that M1 number of missionaries and C1 number of cannibals are on the left hand side of the river, M2 number of missionaries and C2 number of cannibals on the right hand side of the river, and the boat is on the left side. Now, that is my initial state. And you can see after arrow we have L M1 minus M, C3 minus C. What does it mean? It says that on the left hand side M1 minus some M value, number of missionaries are there, and C3 minus C, cannibals are there, and R M2 plus M. So, the M2, remember the original number of missionaries on the right hand side were M2. The left hand side we had M1, M1, M are subtracted, they are added on the right hand side. Similarly, number of cannibals which are C subtracted from the left hand side and added on the right hand side. So, that means M missionaries and C cannibals moving from left hand side to right hand side. This is precisely what we want, and the boat moves on the right side. So, this is exactly what I have on the right side. Now, look at the 4 prerequisites again. What are the MC values? They can be 0, 1 and 2. Okay, we know we cannot have more. Why? Because we can't move 3 people across. Maximum values of missionary and cannibal can be 2. If missionaries are 2, cannibal is 0. If missionary is 1, cannibal can be 1 or 0. If missionary is 0, cannibal can be 1 or 2. Okay. Next one, M plus C can be 1, so one person can row the boat, or M plus C can be 2. So, either 1 or 2 person can carry that boat. Okay. Now, the next one, what is it about? Now, this is very similar to what we have seen before. The number of missionaries on the left hand side must be greater than number of cannibals on the left hand side, or number of missionaries are 0. So, we had M1 before, now we are subtracting M, so that and number of cannibals also are reduced. What does that mean? That means that now we have M1 minus M missionaries on left side, C1 minus C missionaries on the left hand side, that must fulfill this condition. And otherwise, the M1 minus M, now total number of missionaries on the left hand side is 0, then it is fine. Similarly, M2 plus M, the number of missionaries now we are going to have on the right hand side must be greater than or equal to number of cannibals on the right hand side. Okay. So, that the next condition represents that. Okay. Similarly, you can see the move which moves from right to left. An interesting exercise that you can pick up and try out is, can you write a single rule converting these two rules into one? Think of it, it is an excellent idea in fact. Anyway, so let us see what this particular rule is doing. It is almost a replica of the previous rule. The only difference is the boat is on the right hand side and we are moving from right to left. So, basically we are incrementing number of missionaries and cannibals on the left hand side and decrementing from the right hand side, the rest is the same. So, I do not need to describe the entire rule once again, but you can see that it is the same. Okay. Now, the complete sequence of moves, okay, see how it is done. We begin from L33 R00 and BL. Now, we move to L31 and R02. What does that mean? That means that I am sending 2 cannibals on the other side. Okay. And the next 3 columns actually describe the rule applied, number of missionaries moving on the right hand side, number of cannibals moving on the right hand side. You may ask me, how have I decided rule number 1 to be applied? Obviously, because this is the only one rule I can apply. I have only 2 rules, and when I have a boat on the left hand side, I can only apply rule number 1. So, I do not need to worry about that rule, okay. But the problem is, I have to decide number of missionaries and cannibals, which I did. And how have I done it? I have cheated, because I have already solved that problem and I know that this is how the problem is going to be solved. I know that in the beginning I have to send 2 cannibals on the other side, I did that, and that is what I want my program to do actually if I want to write an AI program. But anyway, we are not discussing that part right now, we are discussing only this. Okay. So, let us see that. What is the second one? Now, I am moving from right to left, only the rule number 2 can be applied. So, we have applied rule number 2, and now we are also stating what are number of missionaries and cannibals, okay, and so on and so forth. You can just go through the complete set of movements one after the other. Eventually, you will find that you will have all missionaries and cannibals on the right hand side. Quite interesting observation can be seen from what we are doing on the right hand side. You can see that in the initial movements, first 4 movements, we are not actually moving missionaries. Next 3 we are moving missionaries, next 4 we are not moving them. Now, this is something which is heuristic. A heuristic for this particular problem can be something like this. In the initial run, what we want is 2 cannibals on the other side, okay, and then we want all missionaries on the other side and then moving cannibals on the other side. Now, that is the heuristic. What does that mean? That means that in the initial run, avoid all moves which moves missionary on the other side. So, the preconditions that you use should use M equal to 0. In the middle part, you should try to use as many M as possible, which is legally allowed. For example, if you have 1 cannibal, you can send 1 missionary with it. If you have 2 cannibals on the right hand side, you have to send 2 missionaries on the right hand side, and so on and so forth. So, that is what I mean by legal moves. So, you will have to choose that precondition accordingly. Okay, the rest is simple. We'll look at the other problem called farmer fox chicken grain problem, and precisely what we are trying to address here is called multiple representation of the same problem. How can you represent the same problem in multiple ways, and what are the advantages of one type of representation over the other? Okay, now let us try to understand what the problem is. The problem is about a farmer fox chicken and the grain finding themselves on the one side of the river, and they'll have to move on the other side. Same boat is available which can carry only 2 items. Only farmer can row the boat, obviously grain and fox and chicken cannot. So it's quite obvious. And what we want is, we want everybody remain intact at the end of the problem, and if the farmer is not around, fox may eat chicken and chicken may eat grain. So this is something that we do not want. How can we solve this problem? Now, in the beginning you may feel that the problem is almost the same as the previous one. It is not. There are some important differences. For example, if the only farmer can row the boat, and when the farmer is around, nothing wrong is going to happen. Not only that, the fox will have nothing to do with grain. So if you have fox and grain on one side, absolutely no problem. The first representation. If you are not very good in mathematics, probably it looks a little hard to understand, but this is not so. Please try to understand. Let us look at the first representation: L, FR, FX, CH and GR. Farmer, fox, chicken and grain. All 4 of them on the left hand side. FR is farmer, FX is fox, CH is chicken and GR is grain. And on the right hand side you have tilt FR, means not FR, farmer is not. Okay. So we are using a different notation here. There are many other notations used, there is no standard about this. So you can use one which suits you. So it is not FR, not FX, not chicken, not grain. What does that mean? We have everything on the left hand side. Okay. And the final state is everything on the right hand side. So it says L, not FR, not FX, not CH, not grain. And on the right hand side, FR, FX, CH and grain. So it's pretty simple. You have all 4 of them on one side and in the initial state, or 4 of them on the right side in the final state. That's what the state space representation. Pretty simple? Yeah. Let us look at the state space. Now state space is little clumsy in the sense that we write a lot of like L, A, B, C, D. Now A, B, C, D is what? Maybe farmer, not farmer. A is what? Farmer or not farmer. B is fox or not fox. C, grain, not grain. Chicken, not chicken. D is grain, not grain. Okay. So L is this and R is exactly opposite to this, and that is very important. If farmer is on the left hand side, he cannot be on the right hand side. Okay. Where A belongs to obviously farmer or not farmer, B belongs to fox, not fox, and so on and so forth. So that, what does that mean? That means that each one of the item is either on the left hand side or the right hand side. This is precisely what this particular statement says. But then there are other preconditions. The other precondition is, if A equal to not FR, what does that mean? The farmer is not on the left side. Okay, A is on the left side. Then you cannot have fox and chicken both on the same side. So that is false. And also chicken and grain cannot be on that side. Okay, so fine. If A is FR, farmer is on that side. On the other side you can see that not B and not C is about the other side. Okay, so other side you cannot have that. Okay, so if farmer is on one side, the other side you can't have the fox and the chicken, or the chicken and grain. So that's what this first representation do. The second representation. Now it is a little different. What is the difference? I'm segregating each one. At L, FR. FR is on the left hand side. At L, FX. Fox is on the left hand side. At L, CH. CH is also on the left side. At LGR. Grain is also on the left hand side. Okay, that's the initial state. Everything on the left hand side. And the final state exactly opposite. At R, FR. At R, FX. At R, CH. And at RGR. What does that mean? Everybody is on the right hand side. So simple, fine. It's as simple as the previous one. There is no, you have nothing to choose actually. The first one also is pretty simple, second is quite also. Okay. But then there is some difference here. Okay. You can say that farmer is on A side, fox is on B side, chicken is on C side, and grain is on D. Okay. Where ABCD belongs to LR. Now you can see that part is also quite simple compared to the previous rule, this is more readable actually. And now let us see what the next two lines describe. It says if farmer is on the right side, fx and ch cannot be on the left side, okay, and ch and grain also cannot be on the left side. Now this actually is more readable than the previous one. Earlier we used to write the value of the variable, the variable itself. Now we are writing the value of the variable. We say that at RFR, which is very clear, it says that the farmer is on the right hand side, and at LFX, which is not, it says that fox and chicken cannot be there together on the left side, and chicken and grain cannot be together on the left hand side. Now this is comparatively much more readable. Okay, and the second part of it says that if the farmer is on the farmer is on the left hand side, you can't have the same combination on the right hand side. Okay, so that is something which is more readable. Okay, then we can have the third representation. Now this is a little more tricky. Now what's tricky about this? Try to see and try to understand. The farmer is represented by 1. The fox is represented by 2, the chicken is represented by 4, and grain is represented by 8. You may think why it is done that way. See, earlier we had a problem when we try to make sure that when farmer is not around, this two combination is also difficult to express. In fact, to write that we have used complex notations which are pretty hard to write. So can we simplify that, and this is an attempt to do that. Try to understand. Again let me repeat, 1 is farmer, 2 is fox, 4 is chicken, and 8 is grain. So the first statement, first line which says L1, 2, 4, 8 and R 0, 0, 0, 0, what does it mean? Farmer, fox, chicken and grain on the left hand side, nothing on the right hand side. The second one, L 0, 0, 0, 0 and R 1, 2, 4, 8, same, everything on the right hand side. So these are the initial and final state. Now what is the state space? Now state space is L, A, B, C, D and R, E, F, G, H. Now what those values are? First, A, B, C, D is farmer, fox, chicken, grain. E, F, G, H is also farmer, fox, chicken, grain, but then some other values. If A is positive, E has to be negative. What does that mean? If farmer is on the left hand side, cannot be on the right hand side. But that you don't need to check like the earlier case, not, and all that is just gone. Why? See what we have done. We say that L, A, B, C, D, E, R, E, F, G, H. Okay, and then say A plus E is equal to 1. What does that mean? That means that farmer is either on one side or the other. So A or E, one of them must be 0 because farmer value is 1. So if A plus E is 1, that means either A is 1 or E is 1. Both of them cannot be 1. Okay, so farmer cannot be on the both side. Okay, B plus F is 2. What does that mean? B represent fox and fox value is 2. So if fox is on the left hand side, B is 2. Fox is on the right hand side, F will be 2, but then both of them cannot be 2. That is the meaning. B plus F is 2, that means one of them is 0. Okay, I could actually have written that as well. So either B or F is 0. Okay, C plus D is 4. Again the same logic. C is what? Chicken. Chicken is 4. That values, we have assumed that value is 4. So is either on the left hand side or the right hand side. So the total is 4. That means one of them is 0. Same about D and H. Okay, only the value is 8. Now the beauty of choosing these value can be seen in the next two statements. It says that A plus B plus C plus D not equal to 6, 12 and 4. Now you will be surprised, where is that farmer, present, not present and all that has gone. We don't need to do it. Similarly, E, F, G, H not equal to 6, 12 and 4. Now how can I remove all that? There is nothing which describes the fox to be, a farmer to be on one side or the other. But then we don't need to. If farmer is on any side, the summation is always going to be odd. Okay. What we do not want is fox and chicken. When fox and chicken, fox value is 2, chicken value is 4, total becomes 6. So, when the total is 6, that means only farmer, only fox and chicken is there on that side, which we do not want. So, 6 is not allowed. Okay. What about chicken and grain? 4 and 8, that is 12. So, that also is not allowed. What about fox, chicken and grain, all three of them on one side? That makes it 14. That also is not allowed. So, that is precisely what we say, we disallow 6, 12 and 14. That is all, we do not need to do anything else. You can see that this is a very simple representation compared to all both of the representations before. We just say that ABCD is not equal to 6, 12 or 4, done. EFGS is not 6, 12 or 4, done. Okay. Now, what we are trying to stress here? First thing, it is possible to have multiple representations for the same problem. We have seen 3 representations, but believe me, there are 100 odd representations one can easily write, even more, potentially infinite in fact. Not only that, you can always apply a clear idea to simplify things. Many times the things look pretty complex on the face of it, but if you can think of a clever idea, the presentation becomes much simpler. That is precisely what we are trying to stress here. Not only that, you can define variables and manipulate them in multiple ways. We have seen 3 different ways of doing it. We have seen how you can use a vector, then we have seen how to use a predicate. The example was of a predicate. We will study about predicates later, but when I say L, F, FR, L basically is an example of a predicate. And the third one was a clever mathematical representation. I cleverly defined the values of farmer, fox, chicken and grain, and in fact this is something which is done by many others in computer science. You probably have come across some cases where there is a typical bit which is set for something. Now, here is precisely what I am doing. Bit number 1 is farmer, bit number 2 is fox, bit number 3 is chicken, bit number 4 is grain. And if you look from that angle, it is 1, 2, 4 and 8. So, this is precisely what I am doing. In fact, not only that is better to represent, it is also better to code and run faster. So, okay. So, that is the point, that is the point which I wanted to stress. That is what it is. Some presentations are simpler compared to others. Some presentations are complex compared to others. Some presentation, again, there are 2 things which I am trying to talk about. Simplicity is one, readability is the other. Probably some of you may not be able to read and understand the third representation better than the second one. Second one is very easy to understand. You just look at it and you understand what is happening, while in case of 3 it is not easy unless you get that idea 1, 4, 1, 2, 4, 8 idea. If you get that right, yes, everything else becomes easy, but unless you get that, it's pretty hard. So, readability is the other issue, simplicity is the other issue. If you can combine both of them in your representation, that is the best. One typical solution of farmer, fox, chicken, grain problem is shown. You can see that you begin with all farmer, fox, chicken, grain on the left hand side and so on, and then you send farmer and chicken on the other side. Why? Obviously, because fox and grain cannot do any harm to any other. So, that is what you do. Only farmer can row the boat. So, you get the farmer on the left hand side again, then you take up any one of them. So, I am taking fox, but you can easily take grain on the other side, but the important part is to bring the chicken back. If you do not do that, it will be eaten up. So, chicken is taken back, and then you pick up grain and take it on the other side. If you have taken grain in the beginning, you can take fox right now. So, that is quite similar. You can take the grain on the other side. Now, what is left? The chicken and the farmer, both of them can go on the right side and the job is done. So, if you give some human being this problem to solve, probably he will be able to do it in few minutes. But if you want to write a computer program, probably you will have to represent that thing as the state space which we talked about and do all this jugglery, and also you will have to, in fact here I have not talked about how to represent, how to write moves. I have not written that. I have not written how to move around in state space, how to choose value of variables and all that, like ABCD are the variables that we have used, and we are not actually showing how the variables are manipulated. But those are all things which are part of the representation. Anyway, so humans can do it, but when computers are to do it, they have to convert. The problem is to be converted into state space like we have done, and we'll have to find out the rule and apply that rule. And again, if there are multiple rules, you'll have to arbitrate somehow and get the right rule to apply. Okay, but then there is one more thing. Okay, we have only two rules and we have only few prerequisites so far. But in real case, real problem case, we have plenty of rules. In fact, I was reading about an expert system which had 12 million rules, and that was an expert system which is being used in commercial domain. 12 million rules, think of it. It's very hard. Okay, to write rules, debug them, and once you do that, your computing system has to choose one rule from them. Pretty hard. Okay, you can't check all the permutations and combinations in the real time. There is no panacea. There is nothing which solves all problems everywhere. Okay, so there is no panacea. I will not give you a silver bullet to solve this problem. Nobody in the world can do it, and it is good. You may be surprised. Why so? Because if there is a silver bullet, probably you won't be attending, looking at this module, and I am not presenting one. Okay, so but the point is, heuristics usually help, and we need heuristics, we need rule of thumbs, and that is precisely what we are going to discuss in the next module. Let us summarize what we have looked at in this module before we embark on the next module. We have seen that it is complex to write rules. Not only it is complex to write rules, it is also complex sometimes to write the prerequisites of the rule. The prerequisites of the rule describes the conditions when the rule is applicable. It might contain number of variables, it might contain number of conditions. We have seen two cases. In one case we have looked at missionary cannibal problem, the other case we have looked at farmer fox chicken problem. We have seen number of variables and number of symbols that one can use, and or, and so on and so forth. And we have also seen how one can assign values to those variables, and so on and so forth, to make sure that you start from initial state and reach to the final state, applying various preconditions, checking various preconditions, and make sure that the rule applied in a valid manner. Okay, so it looks simple on the face of it, but it is hard. We have seen it's hard to write preconditions. We have also seen that it is possible to write multiple ways. Okay, a single state space can be represented in multiple ways. The same way, the rules also can be written in multiple ways, and one actually can decide a better representation. If we pay a little attention to it, one can write better the rules and the state space in a better way. So that is precisely what we have done in this chapter and this module.